There we go. Right, welcome back to the... So I think this is the lecture number 4, the 5th in the series, because we started indexing at 0, which is why, by the way, I don't like Python or index at 0 numbers, because it gets confusing. But this is lecture number 4, and I've called it Energy, Work, and Power. And we do believe in the Oxford comma in this household. No, we will not be taking questions. So way back when, at the end of last season, we were looking at moments as a way to sort of quantify rotational force. So previously we did moments. We looked at which were essentially sort of if we apply a force at a point that isn't... Can you post a clip? If you get tech to give you permission for 30 seconds. If you post it through... if you apply a force through something that isn't the center of mass, then you end up with a resultant sort of rotational force. Okay, previously we were looking at moments, which were a sort of a measure of turning effect. So essentially, like, as I say, if you apply a force to a center of mass of something, it just moves the object. If I apply it at the end, I get rotation. But if we want to quantify the force in a different way, we need other measures. So we could look at the resultant effect of the force. So that was sort of the total, and then we have a force applied to something. But okay, apply it through the center and it's going to move. How do we sort of measure that? But what if we want another way to quantify forces? So there are other measures of effect that we can study. Okay. So number 1 is energy. Now, there is a physicsy argument of what energy is. There is the whole wave pilot duality thing, and all of that scary stuff. But for our intents and purposes, we're going to say a very sort of rudimentary explanation of what energy is. There is a more complicated answer out there. We're not going to worry about it for now. So all particles have energy, which we only care about. Again, there are others. We don't care about them. Right, as a sum of potential and kinetic energies. Okay, so a potential energy is something that is stored within it. So think of like a battery, it stores energy. And kinetic energy is the it's the movement, right? It takes in a certain amount of energy for me to move my arm, for me to climb, for me to throw a ball up in the air. The kinetic energy is relates to its movement. Typically, in our case, the only potential energy we consider is gravitational. Where others include chemical, etc. Okay, so again, chemical energy being it's like there's like a potential reactant, or again that sort of battery storage stuff, and I'm being wibbly wobbly fluidsy mathsy stuff arbitrary about it because it's not relevant to this course. Gravitational potential energy is if I hold a ball here, it's stationary, but there is gravity acting on it, pulling it downwards. So if I let go, it's going to fall. And it doesn't have an inherent kinetic energy. The ball isn't causing itself to move. It's that stored potential energy from the height up that is then being converted into kinetic to get it to move downwards. So we write... I'm going to do it in purple so it's quick to find. So our first equation is that gravitational potential energy is equals to mgh, where m is the mass, g is gravity, and h is height. So height here is relative. So if I drop the ball and it lands on the table, I could set the height of the table to be 0 so that when I solve how much energy is lost or gained, I can measure it above a certain height. Okay, we might, value above sea level is less useful to me than value above the floor. But as long as whatever I set 0 height to be in one equation, I use it for the same set of system, it's all good. So note, height is above some chosen 0. So just be consistent. Okay. In contrast then, kinetic energy, so Ke is half mv squared, where again m is the mass of something and v is the velocity. And this is all particle equations, so it starts to lose accuracy when things actually have shape and different parts of it and all this sort of stuff. So assume particle for the minute. So with those two equations, you can see that if we release two objects from the same height, a heavier object, they both have the same gravitational potential energy and they both have 0 kinetic energy. So the thing that is heavier is going to have more stored gravitational potential energy. Because that mgh, if g and h are the same value, m is the only thing that's different, so m is going to be bigger. And we can do a similar argument later down the line when we start looking at conservation of energy, because energy is conserved. Classic joke incoming. I knew it. As soon as I said that we're assuming point masses, it's always the spherical cows. It's always the way. Right. So again, velocity. Again, it's important to note here the velocity is relative to the frame of reference, right? So this is the really cool demo where if you shoot a ball off a van moving 60 miles an hour, the van is moving 60 miles an hour and you shoot a ball 60 miles an hour off the other side, the ball to us stays still because the 60 and the 60 cancel. So when we talk about energies, we need to make sure that we're just being consistent with our frame of reference. Okay? The trick there is the frame of reference of the car. You've shot it, it's backwards 60 miles an hour, so it is leaving you 60 miles an hour. To everyone else, we're just watching it. So we need to be careful with those things. Somebody had to say it, I just took one for the team. Scandalous, scandalous. I tell you what I'm going to do, actually. Okay. I feel like I'm going to use the stress ball a lot today, just from doing lots of demos. So let's go back to green. So hello Cap, how's it going? How are things? We're doing work, energy, and energy, work, and power. Physics. You tire? Mood. Well, learn some maths. That will wake you up, I guess. Sort of. There's lo-fi rock music. Keep you company. Yeah. Okay, so what am I saying? When there are no external forces, the energy total of the particle remains constant. Again, there is a lot of sort of hand-wavy, ignoring the wider context here, but essentially if nothing else is acting on it, aside from gravity, the energy within a particle will stay the same. So that's what I was saying earlier, when we have a gravitational potential energy of a fixed height above, say, the ground here, and we have a fixed energy here. But to go from this energy level, which is mgh, I haven't changed the mass of the ball, I've just changed the height of it, to here, the ball has had to move, right? So it's lost some energy because it's been moving. So as it loses potential energy, it gains kinetic energy. Obviously, I'm cheating because I am moving it, so I'm the external force. But if I just let it go and then catch it again, that was really just, yeah. Then that's that conversion between the two. And then when it's touching my hand, I am the force affecting it as I catch it. Hi Hogan, hey Monkey Man, how is it going? How are we? So this principle of energy conservation is really important, and basically what a load of these equations are going to be, and actually sort of it's another one of our conservation laws. So in fluid dynamics, the sort of two big equations that make up the Navier-Stokes equations are conservation of mass isn't created or destroyed, and conservation of momentum, which we have not looked at yet. That's next time. Go me, momentum and impulse. But those are the two big equations that make up the Navier-Stokes. But there's a secret third one, which is conservation of energy, which is sort of underlying a lot of the work that goes on. And that's just saying energy is not created or destroyed. Obviously, if I affect something, I'm adding something to that system, so to that particle. So it starts messing with it. And again, just to be clear, ignoring gravity. This means to gain kinetic energy, a particle must lose gravitational potential. Energy, okay? Which, another good example of this is if I put a ball down on a flat surface, it might roll a little bit, but generally it'll stay still. If I put it on an inclined plane, it's going to roll down the greatest slope. It's not going to roll upwards. It's just going to roll straight down, and it's able to lose potential energy, gravitational potential energy by going downhill, essentially. Had a student presentation in confounding emotional stress, mechanical information stress, felt great. I don't know if that was the topic of the presentation or if that was how you were feeling from the presentation. But both is good. No? Mildly concerned. But yeah, so this relationship between kinetic energy and potential energy will come back and forward. So, okay, so the ball will roll down the hill, but it's going to have to work against energy to roll up the hill, which means something's going to have to be added in to make it do that. So we need to be able to say or quantify how do we make it gain energy, essentially. So for some reason, the next bit, all I've written in my notes is what does it mean to do work, and I'll just put mood. So so to gain energy, work needs to be done. But what does it mean to do work? Mood. We don't do that here. So, work or work. Work. This is one of those words where I said it differently to people from England, and now I don't know which one is the way I'm supposed to say it, but we get there. Okay, bonus points for the StarKid reference in my chat. I appreciate that immensely. The topic was basically muscles putting muscles under. Okay, cool. Scary. When I was couchsurfing last year, I, in sort of payment or suffering, I wasn't quite sure, the person I was staying with, we basically just binge watched all of the StarKid musicals together, which was wonderful until we got to Me and My Dick, and I was like, no, trust me, this is a good musical. Like, it's a worse sell than the live animated Cats. Better after the fact, but like, trying to convince someone on the premise was an interesting. Binge watch Severance. Bethesda Severance. Oh, this looks really good. I don't have Apple TV. Stark is making a new one. I saw that there was Cinderella in the Giant Castle. Not Giant Castle. Cinderella in the something. Cinderella's Castle. That I haven't seen yet. Don't know if there's a new one after that. But I've seen all the ones up to that point, I think. Except maybe like a few of the Nightmare Time season 3. That was a watch. Yeah, liking StarKid is one of those things where I drop a bit of cat lore and everyone's like, this makes so much sense about your character. And I take it as a positive, but you know. Do with that what you want. Space baby. Ooh. Well, that looks stupid. I love it. Ten out of 10. Thank you. Okay, we're blasting through this. I've got so many exam style questions to keep going. It really do be. So work is the measure of energy transfer from one object another. Okay, so work can't be done in isolation. as proven from the study streaming, work has to be done upon something, or work is done upon you. I didn't want to say that, but I couldn't think what the correct word would be. So if a box is being dragged across the floor, that takes work, but I am the one that's applying the force doing the dragging. So I'm the one doing the work upon the box. In contrast, the box is having work done upon it. That sort of thing. So it is the amount of force applied to the object Sorry, I just had a text from someone saying I'm doing a learn, and I thought they were watching my stream, and it wasn't. It was about something completely different, but I'll pretend that was for me. Anyway, so it's the amount of force applied to the object scaled by the distance the force caused it to move, i.e. our third equation, work is force times distance. Work, force. Okay, so if I throw a ball, ignoring all other things, I'll roll it along a surface. That's what I'll do. I'll give it an impulse, and it will roll along. I've applied a force to it, and it's going to roll, and it will stop. The work that is being done is that distance. Obviously, there are other things in effect here. There's things like the frictional force against me, so it will be sort of the total force, would be the total work done. But if I'm continually pulling something for a certain length of time, so say I pull a box for 20 miles, don't know why I do that, maybe I would, maybe I'm bored, maybe I'm doing DOV. I pull a box for 20 miles, the work would be the force that I was applying as a constant pulling rate, pretend that I do that, multiplied by 20 miles, converted into correct units, because as we know from lesson 0, it's important to make sure that we have the right units so our scales make sense. Can imagine becoming friends with someone who's not. I have many friends who are not doctors. Fun fact. PhDs are a little bit of a time sink in that, you spend all of your time in the same workplace as other people, but I have lots of friends outside of doctorhood. Online even, there's only Simon. Arguably Thomas is also about to become one, but still. I would hate to think of someone that would say no to that question. That's not a nice person. Okay, so work is force times distance. Note here, the work to raise something against gravity is the same as the gravitational potential energy gained by the object. Okay? So if a box starts on the floor, it has a gravitational potential energy of 0. I apply work to it, I apply a force to it to raise it, and then I say hold it above my head for whatever reasons. I say I'm doing a Olympic lift, and I hold it above my head. It's again got no kinetic energy, so it's stationary, but now it's a height of my wingspan What's that called? You're like full with your arm height, whatever that is. I held it above my head. Let's call it 2 meters. Its gravitational potential energy now is the mass of the weight times gravity times 2. But the force that I applied was positive mg. There was no like additional force. It was just enough to lift it, which is its weight, which is mg, times by 2, because I travelled 2 meters. Okay? So we can see that here if I have a nice straight line, and then I have, say here, mg, then the GPE here is 0, and then I apply a force upwards on the box, and now it's here. Its GPE is now mgh, where this is h. And the work that I did, so the force applied, say there was no like additional, like, I didn't use any excess energy, right? It wasn't a proper snatch, that's the word. It was just picking it up. Then the work done here is F times D, which is mg times h, which is mgh. Okay? So that's how I give it potential energy, right? I apply work to it, I apply force to an object, I give it back some energy, and now it is storing gravitational potential energy. So once it's started up in the air, right? So there's a box that has some weight m. It's got GPE of mgh, and it's got ke of 0. So I'm going to put h equals 0 here, h equals h up there. So it's some height above the ground. Well, what will happen is it's going to fall back down and land, right? Earth is going to get in the way. So down here again, as it falls, the energy, no one's affecting it now. There's only gravity affecting it, so we're not adding anything in, which means that we can say that here, so this is 1 and this is 2. We know that energy is conserved. So KE1 plus GPE1 is KE2 plus GPE2. So down here again now, the GPE is now 0, and the KE, so again, its height is 0, so that's why that gets rid of that. And its kinetic energy is some half mv squared. So we have kinetic energy at 1 is 0 plus mgh is equals to half mv squared plus 0. That's my fathom. Oh, I thought you were like, that's what you think. I'm sorry I ignored that comment. I genuinely thought I'd said something and you went, well, that's what you think. But like, in fancy words. I didn't realise you were answering my question. So feet to fingertips held above head. Yeah, that's what I was asking for. Fathom is the distance of your outstretched. I thought that was wingspan. Hi, welcome in. We're doing mechanics. Current question is, if I hold my arms above my head, what's the height? What's that measure? Because if someone... so, from climbing, I keep seeing in gyms, like, your it's really important what your ratio of your wingspan to your height is. Most people don't have wings. Gotta drink more Red Bull, mate. I know, I'm sorry. With the internet, it's safer to ignore comments if I'm confused than respond. So, like, if your wingspan, so your fingertip to fingertip length, is longer than your height, then you have long arms proportional to your body. So you can reach further and get more holds. So that's a good thing to have. I think mine is negative. I think I have quite short arms. I can't remember. I don't have a recommendation for that. I'm sorry. I'm half surprised that as a phrase was allowed to be written. The things that I've permitted, honestly, on the thing. Bananas. My mods go through it and just delete all of my permission. Anyway. Yeah, that was my question. That must be, because, like, Olympic lifting, you care about raising it above your head, so you want to move it less. Because, honestly, the mechanics of, like, powerlifting, I find fascinating. Because there was this whole thing about, like, if you have long femur versus short femur, because where you bend is different because your center of mass has a different, like, we're gonna do something on that. We are definitely gonna do something on that because I find it fascinating. But yeah, anyway, that was a tangent. Let's get back to the maths. What was I saying? Right, we have energy conserved. So at time 1, it's held above the ground. And it has gravitational potential energy and it has no kinetic energy. As soon as it hits, like once it's hit, it stops, obviously. But at the instant where it hits, it has some velocity. And arbitrarily, it's going to keep falling. So this gives us the relationship mgh is half mv squared. So we can kill off those. And what we get is that the velocity is the square root of 2gh. So this is sort of the maximum this is some maximum velocity, and this is assuming that is assuming air resistance. That's ignoring air resistance. Assuming no air resistance. Fingertip to fingertip is 6 foot and you're 5'7". Okay, so apparently that makes you more likely a very good climber because you got long arms. And a swimmer? I feel like having long arms is an advantage in most things. I can't think of an example where having the opposite is useful. Ugh. No spiders. Okay, so whilst having this, oh. I think I'm good. Thank you. The rush to like make sure I click the right button to like turn the audio off. Yeah. So whilst having total conservation of kinetic plus potential is kinetic plus potential across all points in time and space is useful. We don't live in a force-free world, so unfortunately forces. So and what that means is even during free fall there is air resistance acting on it, so that relationship of height at one point, height at another point doesn't exist. So there will be in effect e.g. air resistance, drag, friction, pushing, into the Bristol Channel, poles. So there are loads of things that, like, we interact with the world, right? We have an effect on it. So the whole energy conservation thing doesn't quite work. So work will, in fact, be done. And in fact, what we have is our next equation, which is work done is change in energy. Okay, so that total energy, total object. So as we say, we had to apply some work to raise it up. So that work done was that change in energy, right? The change in energy was adding gravitational potential energy to the object. So that was the total amount of work done. Ooh, enjoy D&D, Hogan. Have a great time. That equation is typically what you're expected to do in any sort of exam type setting where they're asking these sorts of questions, is because it has that... it's quite a nice problem, assuming it's for Bristol Channel. If you're a fan of the Yogscast, there is a meme that the CEO, I think he is, pushes people into the Bristol Channel, which is a river that runs through the centre of Bristol. That is a stupid meme. I think it's funny. So it is a pushing effect that could happen if you accidentally get pushed into a channel. That is, work is being done upon you, and you can figure out how much work by how far out to sea you end up going. So there. Hello. I'm back. I have water, and you can tell because my throat isn't currently dying. Okay, so we have work done is change in energy. What we haven't done is said what the units of work are. So again, if you remember way back when, we said about our quantities and units. So if we look at it, we have work is, so it's newtons for forces times meters for distance. So it's a Newton meter. Or a joule. Okay, so 1 joule is 1 Newton meter, which, if I remember correctly, a Newton meter is a kilogram meter per second, meter squared per second squared. Yeah, kilogram meters per second squared, and then kilogram meter per second squared times meters is kilogram meter squared second per second squared. This is why we came up with joule. This is why that. Showing ads during lecture breaks. Going to talk to the uni president tomorrow. Hey, get off my ideas. This lecture is sponsored by. It's a dangerous path. I have actually seen. I don't know if it was a meme or not, but one of the lecturers on TikTok was playing the game in the corner of the screen of his presentation. You know, the is it called Subway Surfers? The guy that's running along on the top of the trains and moves between the 3 lanes. He just had that going on the side of the screen. And I'm like, it's very, if you can't beat them, join them. But I kind of think it's hilarious and love it. Because if it works to keep attention, it works. Yeah. Unironically, yeah, trying to fit the ad breaks around when we pause. We're trying. Okay. So work is measured in joules. If I forget units at any point, feel free to shout at me. So there is one more thing that I said we were going to do today. We've done energy, we've done work, we got to do power. So number 3 is fight the power. And now I'm on the wrong notes. Where are my notes? Ah! That's also the wrong notes. Come here. So there's only one more thing. I haven't even written anything for this. Love that. Can I be more intellectual with my notes? Okay, so power is the rate at which work is done. And this is now measured in watts. Which is a W, i.e. work per second. So if we're doing work per second, okay, let's do a little derivation of this. Okay, so we're doing work per second, which is the put that back. So power is work per second, which if we look at the units of this, right, so work is Newton meters, and we're doing Newton meters per second. Okay, well, we have newtons, and then we have meters per second. So we have a force, and now times a velocity. And this very hand-wavy derivation. Like, the correct way to do it would be going into, like, well, it's rate of change, so we take a time derivative, and that's why we go from distance to velocities. But, you know, going through the units, you can probably work backwards as well most of the time. So that gives us our final equation, which is power is force times velocity. Okay. So, yeah, essentially you have d, take the rate of change of w, ddw, you get ddx. So that gives us all of our equations. So the equations, in summary, let's do it in blue. We haven't done blue yet. In summary, the equations that we have gained this lecture are gravitational potential energy, kinetic energy, work equation, conservation, and power. So let's see if I can remember those. So we have GP is mgh, ke is half mv squared, work is force times distance, we also have work is change in energy, and then we have power is force times velocity. So we can be a bit more fancy with some of these. So if I label them all, we could also write 4, let's do like 4 star, as work is half mv2 squared plus mgh2 minus half mv1 squared plus mgh1. So that change in energy, right? Energy in the second state minus energy in the first state is the total change in the amount of work done. Normally that would be a negative number. It depends on your frame of reference. So this is work on applied to the thing rather than it going away, right? If I give you something, I've got negative, you've got positive. So we just need to be a bit careful of that. It might be the other way around, depending on which frame of reference we want to talk about. But those are essentially the equations of work, power, and energies that we need to care about for now. So let's do some questions. Number 1. A car mass 500 kilograms is traveling along a straight road. The engine is working at a constant rate of 10 kilowatts. I keep wanting to say kilowatt hours. Don't know why. I'm determined to say kilowatt hours. The resistance to motion is 250 newtons. What is the acceleration when speed is 5 meters per second? So first things first is add in the fact that I missed the units there. There we go. So what would be nice is if we... Kilowatt hours is the unit for the amount of energy used by people. That's why we'll blame Simon. Yeah. In science, we usually use joules. So kilowatt hours and yeah, okay, so it's a measure of work. Then, if it's the same thing. Okay, so first things first, it's always really nice if we have a little diagram. So my car is going to be a box because deal with it. We have gravity working downwards. We're going to assume that way is positive. So we have some pulling force in the positive direction. So we label that F. We're going to label the normal force acting on it. Probably not going to need it right now. There's nothing about resistance. There's nothing about friction, but just so it's there. And we have the resistance to motion as well. And we are told, stop turning it white. That we have some acceleration is in question in the positive direction. Okay. What else do we have? We have that power is 10 kilowatts. So kilowatts, in the same way that kilograms is 1,000 grams, kilowatts is 1,000 watts. So it's 10,000 watts. So a lot of these questions, because they work in sort of cars and they work in sort of bigger values, especially when we talk about power, there will be some unit conversion needed as well. So that is in there. The resistance to motion in total, so we know that R is 250. We know that M is 500. And kilograms is the SI unit, much to the disgust of everyone. Because doing a car in grams would be awful. I don't know how, but I fully just missed with the straw, but I'm just that special. Okay, so these are the values that we have. So the equations that, to my mind, immediately come into play are power is force times velocity. So we also have that velocity is 5. Let's put all our units in to be good. So power is force times velocity, so we can work out what that forward force is. Okay. So we end up with, what do we end up with? 10,000 over 5 years is F, which is 2,000 newtons. Okay, so that gives us our F. So we have F, R, we have mg, N is mg because there's no friction that we know of. Maybe it's not. Other equations that we need to know. So we're looking for an acceleration and we have lots of forces. So we're going to have to call upon Newton's second law. Force is mass times acceleration. Now, annoyingly, I think I've labeled this sort of badly in that this F here is the forward force that is being done by the engine. Whereas this F is sort of the total forces, right? So Ft here is the force from the car engine minus the resistive force. Remember when we were doing Newton's laws, we have to sum across the entire direction. So we have that positive force pushing us forwards, but we also have resistance to motion. So it's F minus R is equals to ma. We now have all of these numbers. So we have 2,000 minus 250 is equals to 500a. So that is 1750 over 500 is equals to A. So 175 divided by 50. So we get A is 3.5 meters per second squared. So that's the acceleration at that moment in time. If there was a different amount of energy being put out from the car, or if it was going faster, the acceleration would be different. But that would be how you go about solving that question. Interestingly, most of the problems that I've seen are sort of constant rates of power. I think variable is a bit more complicated to think of, or you have to start thinking about rates of change, and you start getting into ODE or differential equation territory and calculus, which is not really the goal here. That's not taking the friction into account though. So it is in as much as we are told the resistance to motion, and we don't know what that is. That could be friction, that could be drag, that could be a combination of the two. We just know that the total R. So even though I put N down, we don't know what that is, but we don't need it because we're told the total resistance already. If we were told something about its friction but not told what the resistance is, then we would have to work it out ourselves with more assumptions. But this is sort of helping us skip the steps of figuring out what else is affecting, and we're just told you've got power and you've got resistance. Go between the two. I think the next example then does include more complicated things. So, question 2. A stone of mass 0.5 kilograms is thrown vertically from a point A with an initial speed of 25 meters per second. 25 meters per second. The stone comes to instantaneous rest at a point B, which is 20 meters vertically above A. The stone is subject to air resistance. Find the energy loss due to air resistance as it moves from A to B, and the air resistance is modelled as a constant force of R newtons. Find R, and then state how air resistance could be more accurate. Hi Jules, welcome back. So this is a nice 3-parter. All of these questions, by the way, I found on, where is the typo? Reist. My keyboard is doing a double click, so it's doing its best. Yeah, this is a nice 3-parter because it has an energy question, it has some additional resistance, and then it also has a nice little sort of questiony bit. So these were all taken from, I think, EdXL and OCR A-level papers or AS-level papers. And yeah, there's always some sort of SAE type question. This is just a 1 marker, so it's literally just going to be 1 line, but it's something to think about. And the nice thing with this style of exam question is, like, if you don't get any of the other bits, you can still answer that because have thoughts. So part A. Find the energy lost due to air resistance. So energy loss. Actually, let's do a little diagram first because I like a good diagram, me. So we have something being thrown vertically upwards from a point A to a point B, and it has 25 meters per second here, 0 meters per second here. We have h equals 0. I'm going to set h equals 0 to the bottom bit, and I have h is 20 above. And we're just moving upwards, so we don't need to worry about any sort of tangential, horizontal nonsense going on. Don't know why I put meters per second squared. That's just wrong. Okay. So because we have a velocity, because we have a height, and we have a mass, we can talk about energies. So energy lost is going to be, so it's losing kinetic energy, right? It's slowing down, so it's losing that kinetic energy. And then there's going to be, it's gaining potential energy. So because it's gaining the potential energy that's subtracted from the loss of the energy being done. So you get energy lost is the K loss minus the potential energy gain. Okay? Which is a more complicated way of saying that we're looking at values at A minus values at B. Because we're not talking about the gain of energy, we're talking about the loss of energy. So we have half mva squared minus mghb. So 0.5 times 0.5 times 25 squared minus 0.5 times 9.8 times 20. The stone accelerates with 9.81 meters per second squared downwards. The last person to move wins the game of chicken. No. Times 2 for the return trip, if we were doing the return trip. So the question that we have is from A to B. So no additional effect. If it was total and there was no air resistance, it would be 0. But yeah, for just the one direction, it's just we're going from here and then it's like stopping. No ABBA here. Exactly. And here's one I did earlier. This is 58.25 joules. Hey, Jules is back and we're doing the work question because we're talking about joules and it's joules. I know they're spelled differently, but let me have this. Okay, so that's the total energy loss. So essentially the difference between those two energies. If there was no air resistance, they would be the same. And that's because there's nowhere for it to kind of disappear to. And technically it would travel further upwards, so H would be larger. So we can actually figure out what the difference in height due to air resistance would be if we wanted to play that game as well, which I might do just for fun later. But that's part A. Part B is the air resistance is modelled as a constant force of R newtons, so find R. So because it's thrown up and it has an initial velocity, there's no sort of additional force being done on it. The only force being done on it is the resistance. So we have this R effect moving sort of downwards, right? Even though it's moving upwards, the force is resistant to most motion, right? It's like me trying to push something me trying to slow something down. So I can still use my equation of work is force times distance. So the energy loss, the work done, is 58.25. The force now is the resistive motion, and the distance is 20. For all intents and purposes, I've thrown something 25 miles an hour, and it has taken the air 20 meters to stop it. There's gravity as well. Shush. Ooh, why doesn't gravity play here? Gravity is... Oh, yes. Yeah, gravity doesn't do work. Gravity just exists. Gravity doesn't play in work equations. Times 20. So 58.25 divided by 20, we get R is 2.9 newtons. That's a very snazzy N. Energy lost is 58. 0.5 times 0.5 times 25 squared minus 0.5 times 9.8 times 58.25. Depends on what you're using as gravity. Not what I meant. I don't know what you mean. But when do I ever? Okay, and then the final part of this question is state how air resistance could be modelled more accurately. So air resistance here is modelled as a constant force, and that is not true. Otherwise, it would be walking like sludge, walking through sludge. It'd be like a solid. Air is reactive, and if you think about a balloon, for example, if I have a very loosely compressed balloon, or loosely blown up balloon, I can squeeze it around quite easily. As I blow the balloon bigger and it becomes more stretched, yes, the surface tension has an effect here, but play along, it becomes harder to squeeze. So air resistance increases with pressure, and air resistance increases with velocity. So the faster I move through something, the more pressure I'm applying to it, so it increases. So a good additional model would be, instead of being constant, air resistance should vary, e.g. with speed. Which, if you were doing this as part of a physics degree, you would be caring about the fact that there is a terminal velocity, which is sort of the maximum resistance that air resistance can have. So you go from, like, there is no air resistance on this thing because it's not moving. The air isn't doing any work on the ball, it's just staying still. But as it picks up speed, as it moves down, the air resistance is getting bigger until some maximum, which is this value over here that we worked out earlier, I think. Maybe. I don't know. Let's see what Google AI says. Surface has a maximum value. Yes. That was just half mv squared. Fine. Doesn't gravitational energy is not lost, doesn't factor into resistance calculus, not part of the energy loss bit, which is 58. Doesn't gravitational energy convert from potential to kinetic and back? Maybe. It's been a while since I did physics. Same. It doesn't play here because the work is force times distance. Just disregards anything to do with gravity, basically. I want to drink. Okay. We're going to have a quick break, and then I have 2 longer questions for you. No, I have 3 longer questions for you. No, 1 short one and 2 long ones. It's like we're playing Countdown all over again. But there's an ad coming, and I can't stop it. So, we'll see everyone in 5 minutes, and it gives me time to type out the rest of the questions. So, see you soon. Okay, we have a few more questions, and a bit more time. So let's keep going. Please forgive the trig in text form, but, you know, we make do. So we now have a car of mass 1,200 kilograms moving up a straight road which is inclined to the horizontal at an angle alpha, where sine of alpha is 1/15. Total resistance of motion from a non-gravitational... You can tell that my keyboard is just giving out. Total resistance of motion from non-gravitational effects is given as R. The instant when the engine is working at 32 kilowatts and the car is traveling at speed 20 miles an hour, meters per second, the acceleration is 0.5 meters per second squared. Find the resistance R. So again, first thing is always first is draw a diagram. So it would help if I found my notes. We have... Can we make the car travel a queer road instead? Of course. Much better. We have a box. I don't do cars, I do boxes. Moving up with some power force from the power and some resistance to motion. We have gravity now working not in the direction perpendicular to the direction of motion, mg, and we have some angle alpha. Let's draw a better alpha than that. We have some equations that we want to get used. So we have a power, so let's use P is Fv, and then we also have a balance of forces and an acceleration. So to me that screams F, and again I'm going to delineate by saying Ft is ma. So we have this time, right, we're told that resistance from motion from non-gravitational effects, which means that we're going to have to be careful and include gravitational effects if we need to. Whereas in the previous question, the first question, we were told resistance to motion. Thank you for the follow, welcome in. So now we need to actually be careful of it, and especially now because we're on an inclined plane, there is also some component of gravity working downwards. So here as well, we also have the effect mg sine of alpha, where we split that gravity pulling downwards, parallel and perpendicular to the plane. So find R. First things first. Yeah, let's do it this way. So we have Ft equals ma. So the forces total, we're going to work up the plane as positive. So we have the force from the power minus R minus mg sine alpha is equals to the mass times the acceleration. So we need what this Fp is. Well, over here we can do P is Fp times V. We have that the power is 32,000, and we have that velocity is 20. So that gives us this value of Fp as 32,000 over 20, which is 32,000 divided by 3,200 divided by 2, which is 1,600 newtons. So plugging all of these in, we have 1,600 minus R minus 1,200 times 9.8 times 1 over 15 is 1,200 times 0.5. Okay, and that's just pulling the values down from from the question, there, and there. Something that my maths teacher did always used to say to me, I'm a big fan of like first things first, draw a diagram. They were a big fan of first things first, highlight the question, pull out the values. If we mosey all this around, we get that R is 216 newtons. So that's 1,200 times 0.5, taking that long bit over, minusing the 1,600, you get 216 newtons. So it's not too scary in as much as it's seeing what you have. I think a lot of mechanics, this is why I like mechanics quite a lot, it's sort of seeing what you have in the equation, or seeing what you have in the question, seeing what values fit into what equations, which one of them has the bit that you're being asked to find. We're told to find R, so it's going to be over here. How do we work backwards? To get that bit, we need the force from the power. To get the force from the power, we need the power equation. It's moving in and out of these sort of 5 equations plus F equals ma, because you'll never get away from it. There's always F equals ma. Okay, so those were the sort of quote-unquote simple questions. None of it's simple, but these are getting longer. Instantly spotted a typo. That should be 3 over 4. This is why we don't write equations out. So we have a plane inclined to the horizontal at an angle alpha, with tan of alpha is 3 over 4. Instantly, as soon as I see tan, my brain is going like, right, let's just quickly sock a toe at this, because whenever we have to divide things down a plane, We never need tangent. We always need sine and cos. And normally, the trick is if they give you the tangent, it's because the angles that, or the lengths of the sides that you're being asked to solve have a Pythagorean triplet in them. This felt like a crypto professor after writing a blackboard full of equations saying, see, this is trivial. I'm sorry. I try not to call things easy. I just want to warn you that these next two are harder. Or just longer. They're not harder, they're just longer. It's the same equations as before. That last problem hit my brain telling me it's in motion, having my brain tell me it's at 1%. It is close enough. Oh dear. Okay. What was I saying? Yeah, so whenever I see tan of something, I'm like, right, let's just quickly do that. So if I quickly draw my triangle in a way that lets my thing recognize it as a triangle. For all of the, like, it has shape recognition. It can recognize that's a circle, but it won't draw a blinking triangle. So we have, if that's our angle alpha, tan of alpha is opposite over adjacent. Okay, so opposite is 3 and adjacent is 4. 3 and 4 are Pythagorean triples, which means a Pythagorean triple is Pythagoras' theorem, a squared plus b squared equals c squared, where a, b, and c are whole numbers. So here, 3 squared plus 4 squared is equal to 5 squared. Okay, and there are a few, well, I think the small ones are 3, 4, 5, and 5, 8, 13, I want to say. Five, 12, 13. They're a really cool little thing. You don't need to know that at all. You can do, like, if we need sine, we could do sine of arctan of 3 over 4. And we never need to, like, acknowledge that. It's just one of those things that when you do these equations enough, you kind of see it and you go, right, this is useful. And then I can quickly write down my sine of alpha, if I ever need it, is going to be my opposite over my hypotenuse. So that's going to be 3 over 5. And my cos of alpha is going to be 4 over 5. So just really, it's one of those things. It's not necessary, but it's a nice little side point. Anyway, we haven't even got to the question yet. Particle P is held at rest at a point A on the plane. It is then projected with speed 25 meters per second from A up the line of greatest slope of the plane. An initial model of the plane is smooth and air resistance is negligible. Using this model and the principle of conservation of mechanical energy, find the speed of P at the instant when it has travelled a distance 25 over 6 up the plane from A. In a refined model, the plane is rough with coefficient of friction 3 over 5. Find the speed of P at the same instant as in part A. Essentially, the whole plane inclined greatest slope thing is just a way of saying, so a plane is like a rectangle, essentially, and it's saying that I've angled it here to the horizontal. The greatest slope is going to be up this way. So it's a fancy way of taking something that exists in 3D and making a sort of 1D problem. So once again, drawing it is helpful. So we have a particle at a point A and we have a particle at a point B. So here is our point A. Here is our angle alpha. It's actually the origin of it, I believe. And we have point B here. We have that the speed here is 25 meters per second, and we have that the speed here is 0 meters per second. I just closed my notes, which is a terrifying concept. We also have that it's the distance between A and B is 25 over 6 up the plane, which means, annoyingly, that it is, ooh, don't like A being there. Let's draw that elsewhere. It is this length here that is 25 over 6. So just something to keep in mind when we start doing gravity stuff, we either need to say that gravity works down the slope and it's g sine of alpha, or we need to keep in mind that when we talk about height, we want vertical height here. So we don't actually know what h is. So we can do either or. I like thinking of gravity working vertically downwards. I don't always shift frame of reference to be like along the plane, but you could do that. For this, I think I did it this way. So it's held at rest, and then it's projected, yeeted up the hill, 25 meters per second. So just going through everything and checking I've got everything. Line of greatest slope. Smooth and negligible. We're having a nice time. Use this model and the principle of conservation of mechanical energy. So we're mostly in an energy space. There's no air resistance. There's no resistance to motion. It's only gravity working against us. So we have no resistance / outside force. Actually, I'm going to write this underneath and do like part A, because I'm about to say something completely different to that. I think it's resistance is futile is the saying. So use energy conservation, which says, so we have half mva squared plus mgha is equals to half mvb squared plus mghb. And I'm using the subscripts a and b to be like at the point A and at the point B. And what I'm going to do is I'm going to say that this is equals to 0. This is equals to 0. This is equals to 25. Screenshot these and make a Reddit where you include all your solutions and problems. So these equations, these questions I didn't write. I've taken them from British exam boards. Shh, don't tell anyone. I would happily post more the solutions somewhere though if people were interested in them. Don't know where would be best for that. Hey cat. Right, now we need the height of B. So I'm going to go into my trig world again, and I've got my alpha, and I've got 25 over 6, and I've got h. So I have that sine of alpha is equals to h over 25 over 6. So I have that h is 3 over 5 times 25 over 6. So h is 5 over 2. There's still good information to observe on Reddit blogs. Oh, fair. I've never thought about posting to Reddit, to be honest. So we have that the height at B is 5 over 2. So 5 over 2. So that leaves us with... we don't actually know what the mass of the particle is. M is, who knows? You'll notice that every single term here both have mass in it, right? The heavier something is, the more it moves. Unless forces are acting on it, it don't matter because we just cancel through all of them. So we get 0.5 times 25 squared plus 0 is equals to 0 plus 9.8. What was the question? What am I doing? Find the speed. It's not 0. For some reason in my brain, I was fully convinced that it was... even when I do it properly, I still get them wrong. I was fully convinced that it was finding... It was a balance again. I'm like, wait, this does not add up. So we have half VB. So 0.5 VB squared plus 9.8 times 5 over 2. Okay. So we balance this equation and we get 25 over 2, 625 over 2 minus 9.8 times 5 over 2, 49 is over 2 is VB squared over 2. Again, we have a load of 0.5s, so we can yeet those. So we get 625 minus 49 is 576. I am reading the answers off, by the way. I am not this good at mental arithmetic. So VB squared is VB, sorry. So the speed at point B is 24 meters per second. Ta-da! However, if there is air resistance, then this equation doesn't hold anymore. So we need to do something a bit more intelligent. So with air resistance, oh no, it's not air resistance, it's friction. So with, where did you go? Come back here. With friction, where mu is 3 over 5. So the coefficient of friction is 3 over 5. So frictional forces are resistive. So we have the force due to friction is mu n, where n is the normal force. Okay, so now we have some force up the hill. We have some frictional force working down the hill. And we have n. Okay, and this is at point B. We also know now that we're moving upwards with 24 meters per second. So the normal force is going to balance with gravitational force. So gravity works downwards as mg. So it's going to be mg cos of alpha. Okay, splitting that gravity downwards into 2 parts. Which gives us that the friction is 3 over 5 times 0.5 times 9.8 times, and we worked out what cos alpha was earlier, 4 over 5. Equals 12 over 25. 3 over 5 times 0.5 times 9.8 times 4 over 5. 294 over 125. Gross. I'm just going to write it as 12 over 25 mg and pray it cancels down the line. We then have work done due to friction. Okay. Which is equivalent to energy loss due to friction. So this is work is FD. Now, in the first part of this question, we needed the height to be vertical, right? We needed that h upwards because we're talking about gravitational potential energy, which only cares about the direction of gravity. Work done on the slope, like by the ball, is just distance traveled. It doesn't care about direction. So now we are talking about that 25 over 6, not h. which I think was a big sticking point with this question. So we have that the work done is that frictional energy, so 12 over 25 mg times 25 over 6, and this is why I left it as 12 over 25, because we can do something nice here where we get 2 mg joules. So the work done due to friction, or the energy lost due to friction, is 2 times 2 mg. So we have the work, the energy loss is the energy at A minus the energy at B. Yeah, because it would be energy gained in the other direction. So we have 2 mg. Energy at A, there's no gravitational potential, so it's half mva squared minus half mvb squared plus mg. Cat! I saw your Matt Parker's Secret Santa video. I was there. Hello. Something does add up 22 does not equal 12 times mg. The mg here are values. They're not constants. That's not milligrams. It's not units, sorry. So I substituted in m and g and then came back. Yeah, I did the thing and I got the thing. Where'd it go? This was my Secret Santa present. It was really lovely. I was very happy to be involved. I was very bad at sending videos of me rolling dice and doing things, unfortunately. But yeah, I was in a Secret Santa with a bunch of really cool people and they're all really awesome. So that was exciting. It was the ultimate Zoom call. I didn't know who was going to be in it. I thought it was the same crew as... So I did one 2 years ago with Kate Steckles et al. Similar idea. So I got an email from Matt being like, hi, I'm doing this one. You want in again? And I'm like, yeah, cool. And then suddenly there were lots of people there. I wasn't expecting so many. But it was dope. It was really, really dope. They were all very, very lovely. And there was a lot, like... I mean, the video kind of covers how confused we all were by the concept, but like we were there for about an hour trying to figure out what was going on, which was quite fun. As well as, hey, can I break it in this way? And Matt just being like, no, stop it. Okay, how do we stop you doing that? How do we stop this happening? How do we get Brady to know what a number is? You know, the normal questions that we ask. Yeah, it was a lot of fun. I hope this year brings many more collabs with many more awesome people. Okay, let's keep going because I think we're going to do this question and then finish up. So HB. So we have the energy at A minus the energy at B, and I'm praying that I've got my signs right with this. We have two mg is 0.5 times 0.5 times... Oh no, we don't know what m is. Don't know what m is. Getting all my equations confused. So 2g, 2 times 9.8 is 0.5 times 25 squared minus 0.5 times 24 squared. Add 9.8 9.8 times HB, which we worked out was up here as 5 over 2. Okay. And I've plugged in everything. We don't know what VB is. I'm adamant to just put values in. We're solving the same thing again. Gosh. Right, 2 times 9.8 minus 0.5 times 25 squared. Minus 292.9, taking the 0.5 times 25 squared over, is equals to minus 0.5 VB squared minus 9.8 times 5 over 2, 49 over 2. So minus 292.9, add 49 over 2. This is looking like a really disgusting number. 268.4 is minus 0.5 VB squared. Well, I don't think I messed the signs up because we can cancel through those. So VB squared is equals to 268.4 times 0.5 divided by 0.5, which is times 2. So square root 268.4 times 2, which is 23.2. Yay, that's what I thought it should be. Meters per second. Okay, so adding in air resistance, we've changed from a velocity of 24 meters per second to a velocity of 23.2 meters per second. So it hasn't had that much of an effect on it, but it has had some effect, essentially. Yeah, probably best. Thanks, tech. Appreciate it. So it does make some additional difference. Adding in, so not air resistance, friction. I'm adamant to not know what this question says. But yeah, it's very cool. So a higher coefficient of friction, a higher effect of air resistance. If we added air resistance on top of this, it would be slowed again because it's more work being done against the direction of motion. So just to summarize where we've been today, if I shloop all the way up here, we briefly chatted about the fact that historically we've done moments. So now we've done Newton's laws, we've done kinematics, we've done quantities, we've done energy, work, and power. So we've done lots of things. And then we had a chat about energy. So specifically looking at mechanical energy, so kinematic and gravitational potential energy. So energy due to motion and energy due to height, basically. We touched on the fact that both of those were relative, so you have to be within the same frame of reference. We can't say that two things have the same energy at different height levels, because at this one we set h as 0 and at this one we set h as 0. They then don't have the same energy relative to each other, so we have to be careful on that. When we ignored gravity, and we said there were no external forces, so gravity is a constant force, so we can kind of just ignore it. The energy stays the same, which means that we can look at a particle at one point in time and take its gravitational potential and its kinetic energy and sum that as its total energy. And we can do it at another time, and that total energy should be the same. And that's how, when we throw things up and down, when there's no air resistance, they go back exactly the same place. However, forces exist, the world exists, so work is done. Energy is lost, energy is transferred between two objects. So when work is applied, it is a transfer of energy. If I'm doing work on something, I am applying an energy to it. It is gaining energy, I'm losing it. Mood. So it's the measure of energy transfer from one object to the other. It is equivalent to the force times the distance, or the change in total energy. So if I lose energy by falling, by pushing something, then that has gained that energy. So the work to raise something up is the same as the amount of potential energy it has just gained by, from its perspective, mysteriously appearing in the air from where it was before. Work is measured in joules. Energy is measured in something else. The fuck is energy measured in? I can do this. Mass. Kilogram meters. Look at me using my critical thinking skills. So, mass is in kilograms, height is in meters, gravity doesn't have one. Kilogram meters. I can always tell when it's time to end the stream when my throat starts just completely giving up. Work is measured in joules, and then we talked about the fact that it was the change in total energy. So this is the concept of, or the principle of mechanical conservation of energy. So energy is conserved, total object, no change, no work. If work, then change. Pretty standard. Finally, we talked about power. Gotta have power. It's the rate at which work is done. So we could take the derivative with respect to time. It's the rate of change over time of the work. It is equivalent to a Newton meters per second, work per second, force times velocity. So how much force, how fast is it going? More force, more power, faster, more power. Think cars are the go-to example for thinking about power things. And that gave us these 5/6 equations, which were pretty standard in any question that's going to ask you about work, energy, or power. Your 2 equations of energies, your two equations of work, 1 equation of power, and always Newton's second law is very useful to have. And finally, just writing out what the change in energy is. Then we did some nice questions, and we had a good time. And I think that was everything. So there.